Good day everyone, today I will present to you about one of the antimicrobial agents, which is Meropenem. Meropenem is a semi-synthetic derivative of a natural compound, also classified under broad-spectrum carbapenem antibiotics, given by intravenous IV injection. It has been clinically approved in the US since 1996 and is used to treat serious bacterial infections, including skin, soft tissue, abdominal, urogenital infections, and sepsis caused by susceptible bacteria. Some people will experience side effects such as diarrhea, nausea, and vomiting. Also skin rash and pruritus from Meropenem. In 1976, a groundbreaking discovery was made. Scientists isolated a powerful compound called thionomycin from Streptomyces cattleya. This early carbapenem antibiotic showed potent antibacterial properties, but it came with a problem. Thionomycin was highly unstable in aqueous solutions, sensitive to mild base hydrolysis, and highly reactive to nucleophiles. To overcome these limitations, researchers began modifying thionomycin. This led to the development of the first carbapenem antibiotics, imipenem and panipenem. However, these compounds weren't perfect. They were susceptible to degradation by an enzyme in the kidneys known as renal dehydropeptidase I, or DHPI. To counter this, imipenem was co-administered with cilastatin, a DHPI inhibitor, to prevent breakdown and maintain therapeutic levels. Further innovations came from Sumitomo Pharmaceutical, leading to the next generation of carbapenems, Meropenem. Structurally related to thionomycin, Meropenem featured a key modification, a 1-beta-methyl group on its carbapenem nucleus. This small change made a big difference, enhancing stability against DHPI degradation, and allowing Meropenem to be used without the need for a DHPI inhibitor. Let's take a closer look at the chemical structure and stability features of a key carbapenem antibiotic. This compound has the molecular formula, C-hydrogen nitride penta-oxygen monosulfide, and a molecular weight of 383.5 grams per mole. What makes this molecule particularly effective is its enhanced stability, both against beta-lactamase hydrolysis and renal degradation. Stability against beta-lactamase hydrolysis is provided by several key features: a carbon atom at the C position, a hydroxyethyl group at the R2 side chain, and a trans configuration between carbon atoms C5 and C6. Helke-Bakua. These structural traits prevent enzymatic breakdown, helping the antibiotic maintain its potency. This molecule also resists degradation by renal dehydropeptidase I, or DHPI, thanks to the 1-beta-methyl group attached at carbon 1. Meropenem is a powerful beta-lactam antibiotic that interferes with bacterial cell wall synthesis, ultimately inhibiting bacterial growth and leading to cell death. For example, in Pseudomonas aeruginosa, Meropenem penetrates the bacterial outer membrane through specific porin channels, primarily OPRD. Once inside, Meropenem binds tightly to penicillin-binding proteins, also known as PBPs. In P. aeruginosa, Meropenem mainly targets PBP2 and PBP3. These PBPs function as transpeptidases, enzymes essential for creating crosslinks in the peptidoglycan layer of the bacterial cell wall. By binding to PBPs, Meropenem inhibits transpeptidation. Failures to recognize the pentapeptide chains lead to inhibition of cross-linkage in peptidoglycan layer. As a result, the bacterial cell fails to form a strong and rigid cell wall. As P. aeruginosa continues to grow, internal osmotic pressure increases. But the weakened cell wall cannot withstand the pressure, leading to osmotic lysis and bacterial death. Meropenem resistance is increasingly reported in pathogens like Enterobacteriaceae, Pseudomonas aeruginosa, and Acinetobacter baumannii. These bacteria may exhibit resistance toward Meropenem by T. downregulation of outer membrane porins. For example, in P. aeruginosa, mutations in the OPRD gene lead to downregulation of OPRD porin channels. This reduces Meropenem uptake, resulting in low-level resistance. Next, it may be caused by efflux pump overexpression. For example, in P. aeruginosa, the overexpression of efflux pumps like MEX-ABOPRM and MEX-XYOPRM, which actively expel Meropenem, lowering its concentration before it reaches PBPs. And lastly is penicillin-binding protein active site alteration. For example, in Streptococcus pneumoniae, mutations in PBP2X and PBP1A reduce Meropenem binding. This allows peptidoglycan cross-linking to continue, despite the drug's presence. The cost of Meropenem in Malaysia varies based on brand, dosage, and pack size. Here's a summary of the price range per vial. Meropenem 1 gram injection costs between 60 Malaysian ringgit to 75 Malaysian ringgit. Meropenem 500 mg injection ranges from 37 Malaysian ringgit and 50 sen to 52 Malaysian ringgit. With that is all from me. Thank you for your attention. For references, you can scan the QR code here.